works as a mic, right?
Sorry?
Those works as a microphone for Zoom people.
Yeah, I think so. Yeah, I can hear you when I join. So welcome everyone to today's TAPU seminar. So today we have Sasha Chernoglazov from the Institute of Advanced Study here today to tell us about the radiation processes in the magnetosphere. So welcome, Sasha.
Thank you. Thank you. Yeah, please, particle that corner. Let me know if you can hear me.
Can you stand up?
Oh yeah.
The room is not very good.
Okay, yeah, I can try speaking. Yes. So yeah, just let me know if you cannot hear me from that part. I will try to loud my voice once again. And today again, I will talk a bit about the radiative process in pulsar magnetospheres. And my talk, yeah, if it doesn't have, will be split in three main parts. Except the introduction, I'm going to talk about the magnetosphere, the emission from the current sheet, magnetospheric current sheet, which is responsible for the highest energy emission up to gigaelectronvolts in the energy range of the photons. Then I will go a bit closer to the star and I will discuss how the polar discharge works, which is supposedly responsible for the radio emission, for the production of the coherent radio emission. And in the later stage, I give some sort of ideas how these models combined can be responsible for the production of the highest yet measured emission from the Vela pulsar, which reach 20 TeVs. I believe everyone here knows what the pulsars are, but just to be sure that we're all on the same page, the pulsars are rapidly rotating neutron stars with very large magnetic field, and they were detected as a burst of extremely stable radio emission in 1967, which were associated with the beams of the radio emission going directly to the observer when the star rotates, and the energy which powers this emission comes from the radiation, from the rotation energy of the star, and the star is spinning down. It can be actually measured like over thousands and thousands of radiation periods. We can see that all of the pulsars lose their energy, and they can be plotted on this PP dot diagram, which shows the rotational period of the star on the x-axis and their spin down, the derivative of this period on the y-axis. And the higher the pulsar is on this diagram with these magenta lines, the more energy it loses. And some of these pulsars, which are shown by these blue triangles here, they are detected in the gamma ray. They lose that much energy that some of their energy goes into the emission of the gamma ray photons. Okay, how this energy from the rotation is taken into the emission is probably connected to the idea of the magnetosphere around the neutron star, or the region which is penetrated by the magnetic field. And the simplistic representation, the magnetic field can be thought as a dipolar magnetic field, which starts and ends on the pulsar and correlates with the neutron star. It was quickly realized, though, that this rotation should drive some electric field, which extracts the particles from the stellar surface and propagate them along the field lines, which in turn leads to two different consequences. The first one is the flowing charged particles create the magnetospheric current. And the magnetospheric current creates the toroidal magnetic field, which is shown in here. And another part is because the magnetic field lines are populated with plasma, they cannot further correlate with the star beyond a certain radius where the gravitational speed is equal to the speed of light. So this surface is called the light cylinder, which is shown here in orange. And if a field line crosses this cylinder, it has to change its geometry and starts opening up to the infinity. And the regions of these open field lines, they are organized as the open field line zone, which is anchored to the polar cap zone on the stellar surface, and the closed field lines where pretty much nothing interesting happens. So this electric and magnetic field, the polarized electric field and the toroidal field create the Poynting flux, which flies away and then re-emitted in the forms of different electromagnetic emissions, starting from the radio emission, which is with the energy of a few 10 to the minus 6, 10 to the minus 7 electron volts, and up to hundreds of GeVs, or even now tens of TeVs. So pretty much like 20 orders of magnitude of the emission. To understand where the different emission comes from, it's useful to look at the phase resolved light curves of the different energy ranges of the pulsars. So this is the same pulsar with the beginning, with the left and the center to the radio peak. So we can see some radio peak is in here. It's not very well seen, and the second one is here, just in the center. And then there are the optic range, which is electron volts, and there are the gamma rays from hundreds of MeVs and even more. So it's believed that this first narrow peak, isolated narrow peak of the radio emission comes from the narrow bundle of the open field lines close to the stellar surface and this polar discharge zone, which I'll discuss in the second part of my talk. And this broader emission, more high energetic emission, comes from the magnetospheric current sheet, where the open field lines of the different polarities just meet each other and reconnect, releasing their magnetic energy into the energy of the particles. So this is how the system looks like in the numerical simulations, with the central part being the light cylinder with the closed field lines, and this is the magnetospheric current sheet. And the conditions in this current sheet are so that like the magnetic field there is that large, and also the particles are that energetic, that the radiation losses cannot be longer neglected, and it becomes, they start affecting the dynamics of the particles significantly. How it happens? Because the radiation losses are proportional to the amplitude of the magnetic field to the second degree, and also the Lorentz factor of the particles to the second degree. And the radiation, the reconnection drives the electric field, which is large-scale electric field proportional to the magnetic field amplitude. And if the radiation losses are balanced by this acceleration force, which is a typical acceleration force on the pulsar or in the current sheet, then we'll speak about this regime as a radiation-reacted limited regime with the Lorentz factor gamma sin in here. And I'll further use this gamma sin comparable to the magnetization sigma, which is the ratio of the magnetic field energy density to the particle energy density. And for the realistic pulsar parameters, for some of them, this gamma sin even smaller than sigma. Why it is important, I'll show a bit later. So let's switch now to the first part of my talk about my kinetic simulation of the current sheet, with particle and cell simulations, where we allow some pretty large separation of scales, and also with the pretty large magnetization of the upstream around 50, which makes it relativistic current sheet, and also vary the cooling strengths from gamma sin to sigma around 0.2. So gamma sin is significantly smaller than magnetization sigma, which we call it. Yeah. The magnetic compactness here, I don't think it makes it's very important here, but I think it's even smaller than 1. And it's much larger than 1, sorry. Yeah. So it's strong cooling. Its magnetic compactness is going to be larger than 1 for all of these parameters. Yeah, and up to gamma sin to sigma around 5, which is, I will refer as a weak cooling. So here is the typical snapshots, the density snapshots of the current sheets with the weak cooling on the left side and the strong cooling on the right side, with the volume rendering showing the density distribution. And also note that the color bar is a bit different for weak and strong cooling. Actually, not a bit, but almost like order of difference, because the compression for the strong cooling current sheet is much larger than for the weaker cooling. And the field lines here showing the magnetic field with their amplitude color coded. Overall, the structure of this current sheet looks pretty similar to what we know from 2D simulations of the reconnection, of the relativistic reconnection, with the X points where the magnetic field actually changes its geometry, reconnecting from the different upstream zones, and these flux tubes in here where the exhaust from these X points accumulates. But also there is something new in here. So these ripples, which can be manifested in density, actually new.
Can I ask you to use the stick to point? The cursor is not very good.
Yes, I can try, but then I'll need to rearrange my setup a bit because it's stretched that. Is there like a laser pointer or something just to switch between slides? Okay, yeah. Let's try to do it. Let's see how. Okay, so here is the X points. Like here is one where the magnetic field is torn apart and reconnected with the magnetic field which goes from the other part. So similar here. And there are these structures of plasmoids where well, they are very dense and they accumulate the exhaust from these field lines, or whatever is pushed by the magnetic field lines. And some of the structures, you can see that there are some like ripples on the perpendicular to the upstream magnetic field direction, which manifests the drifting instability. This is a new sort of 3D instability, which is important on here. Except the different thickness of the current sheet, or like the puffiness of the current sheet, also the particle dynamics in there is varying, which can be seen from the spectrum behavior or the distribution function behavior of the particles. For the weaker cooling strengths, which are shown by the like warmer colors in here, the spectrum is much more extended. It pretty much reaches this, reaches the cutoff at the Lorentz factor corresponding to the radiation reaction linked at the Lorentz factor gamma c. But for the stronger cooling, which starts from 1 and goes down to 0.2, something like this, the spectrum is a bit more steep, it's shorter, but still it reaches larger Lorentz factors that are allowed by this radiation reaction limit region, pretty much with the cutoff and the energies comparable to magnetization C. So there is some mechanism which accelerates particles more efficiently than the radiation losses somehow for the stronger.
What are you assuming for the ratio of pairs to ions?
Sorry, about the science?
But you must have assumed something about the pair multiplicity.
So the ions here, okay, ions here is just a small fraction. They added here as particles of mass 1 because it's all relativistic. And the mc squared gamma here is pretty similar for.
But what was, are you self-consistently doing all the pair production all the way out, or are you just inputting a pair?
Yeah, I'm just inputting them as a small admixture of.
They're asking what is the number?
Here it's like 1% of mass. Here it's like 1% of mass, the fraction of ions.
So you're going to pair multiplicity.
Yeah, that sounds like this. Yeah, I will discuss it briefly in the second part of my talk, which we should expect as a realistic admixture of ions. Okay, so the takeaway from this slide is that for the stronger cooling, it's actually possible to accelerate particles to the Lorentz factor larger than this gamma c, the radiation reaction limit region, while it's likely impossible for the weakly cooled current sheets. And to understand how this happens, how the particles can get accelerated above the Lorentz factor, which is seemed to be like the theoretical limitation. We trace this story for one of the particles which reached one of the highest energies during its lifetime. So here on the left, I show the different stages of the particle evolution. Initially, it's being slowly dragged towards the current sheet together with its host field lines, which is shown in blue in here. Then it passes through the acceleration phase at the X point of the injection phase, where it gets the Lorentz factor, which is shown in here, pretty much comparable to magnetization sigma. Then experiences multiple scatterings within the current sheet, like losing and gaining some energy. And closer to the end, it approaches the plasmoid and accelerates to some higher energies, the highest energies achievable before hit the plasmoid and get stuck in there forever. So on the right, this is the video which shows one of the those weak scattering events when the particle loses some small fraction of the energy. With the color again showing the plasma density, and the field lines showing the magnetic field, and this rod which is sticking out, this is the direction of the velocity of the particle. So the particle is initially accelerated by the X point, and then it's being scattered on these drifting instabilities, which leads it to losing some of the energies, which it moves along the null surface where the field equals to 0, but then it eventually hits the upstream magnetic field and loses some parts of its energy. And at the later time, it gets collimated together with the bent magnetic field line with a slingshot-like mechanism towards the plasmoid. And then it will go to the second part of its evolution. And at the later stages, the particle is being dragged towards the plasmoid by this shrinking loop of the magnetic field with a slingshot mechanism. And then it hits the plasmoid and loses all of its energy. Most interestingly in here, that it not only reaches the highest Lorentz factors, which even exceed the magnetization sigma, but also the loop is oriented in the direction of the upstream magnetic field, which might be interesting for the reconstruction of the anisotropy of the emission, from the energy-dependent anisotropy of the emission of the current sheet, which is particularly important for our understanding of the light curves from the pulsars. So, in order to rescale our simulations to the light curves, which you can expect from the current sheet, it's important to know that the photons which move from the radiation reaction regime actually emit the photons of the characteristic energy comparable to 16 MeV, which is already pretty soft but still gamma rays. And they are proportional to the amplitude of the magnetic field and also to the ratio of the Lorentz factor of the particles versus gammas. So for the most energetic particles, which Lorentz factor is much larger than gamma sin, we expect harder emission, which exceeds this theoretical limit. And for the energy dependent anisotropy, which is shown here with x angle between the upstream magnetic field and the wave vector of the photon, and here the y-axis is the energy, we can see that actually most of the energetic emission happens for the strong cooling in the first place, and no energetic emission happens for the weak cooling. And also most of this strong emission is collimated in the direction of the upstream magnetic field, which is unsurprising because the most energetic particles are flying together with the shrinking loop, which is in the direction of the upstream magnetic field. And when they hit the plasma, they emit the photons in the same direction. For the scaling, but also now we know that the most energetic emission is produced by the strongly cooled current sheets. But the question is how the energy of this peak scales with the energy of with the efficiency of the cooling. Because from the primary, it can be naively assumed that this scales as the gamma sin to the -2nd degree. But actually, the particle cannot move in not radiation reaction limited regime. It still moves in this regime when any acceleration force are balanced by the cooling force. But it's just dictated not by the upstream magnetic field, but by the local conditions of which the particle feels. Which means that this acceleration force by the large scalar connection electric field is balanced by the radiation losses dictated by the effective perpendicular magnetic field, and which scales inverse proportional to the actual Lorentz factor of the particle. And this plot here shows actually that very few of the particles are instantaneously above this theoretical limit, which probably are strongly cooled, catastrophically cooled, and lose lots of energy almost instantaneously. And from these plots of the synchrotron spectrum for the current sheet, we can see that, again, with the color showing the cooling efficiency, the weakly cooled current sheets produce very short spectra with very short cutoff, while the strongly cooled current sheets produce more extended spectra, which hits the energies of even thousands of MeVs. And the position of the peak actually scales linearly with the cooling strength as is predicted, as can be shown from this inset with this line showing the linear dependence and the dots showing the position of the cutoff of the different cooling strengths. Okay, this plot shows how the emission is distributed across from the current sheet for the different cooling strengths. This is for the similar snapshot as I showed on one of my previous slides, on the first slides. So this is the weak cooling again, this is the strong cooling to the right, and the green color here shows the emission which is produced by all photons, and the blue emission on the right half of each of the snapshots show the emission above this 16 MeV theoretical limit. Kind of unsurprisingly, for the weak cooling, this emission is puffier, it comes pretty much from everywhere, and it's reasonably soft, so almost no hard emission is produced. So this part with the blue insets is almost empty. In contrast, for the stronger cooling emission, this emission comes from some isolated zones, which actually can be seen being pinned down close to the edge of the plasmoids, because they are produced by the particles which bombard the surface of these plasmoids and emit the energy, as I showed in one of my previous slides. And most of the energy actually goes into the hard emission. So we can expect from the strongly cooled current sheets in pulsar magnetospheres, we can expect some more energetic emission. And also know that the color bar here are different again because radiation losses for the weak cooling are much less significant, much less important than for the strong cooling. And the difference here is like almost 20 on the color bar.
So in this simulation, you kind of resolve the gyro motion to do this.
Yes, we have to resolve the gyro motion.
Yes, but do you account for the secondary pair productions? Or what
No,
is
here there is no QED at all.
Oh, I see.
So we
do you
just
expect any kinds of QED for this happening?
here, yes, it's likely possible. Yeah,
So
but
the optical depth probably is like
optical depths might not be that large. Actually, for Vila like pulsar, it's very small. It's around 10 to the minus 6. But for the crab, it's catastrophic. Yeah, it's just. But for Vila, even though it's very inefficient, still the number of the emitted photons is that large that it produces some significant correction to the magnetization. Okay, so now I would switch to the second part, discussing how this our understanding of the emission, synchrotron emission from the current sheet, can actually be applicable to the real observations. Speaking about very recent, now already not that recent observations from by the Hess collaboration, which measured 20 TeV emission from the Vila pulsar in this part. What we can see from here that this, the first part of this spectrum, is very similar to what we saw from the previous, from my previous part of the talk, and it's likely produced by synchrotron emission from this current sheet. If we use this analytical formula for the scaling of the position of the cutoff, which is here the range of a few GeVs, and playing with the numbers, we can see that the required magnetization of the upstream for the given efficiency of cooling this radiation reaction limit gamma C around 10 to the 5, the magnetization of the upstream must be the light cylinder, so here, must be around 10 to the 7, which is actually good news for us. Because the particles, as we saw, the particle in the strongly cooled regime, the particles can move with the largest Lorentz factor comparable to magnetization sigma, which means that they have the energy of around 10 TeV. And if they inverse Compton upscatter some of the soft photons, which are flying around this current sheet, this inverse Compton upscattered photons should have the energy also in the range of 10 TeVs, as we would like to have, to explain this 20 TeV emission. But there is a small problem in here. According to the standard understanding how the pulsar magnetosphere works, it populated with plasma from this polar discharge zone, which produces that dense plasma with multiplicity or the ratio of the magnetic the produced plasma to the some typical Julian density plasma around 10 to the 5, 10 to the 6. And then, if this plasma ends up close to the current sheet, it means that the magnetization falls dramatically up to the 10 to the 5, which is a couple of orders of magnitude below our desired one. And in order to resolve this problem, we probably need to better understand how the discharge might work, how the polar discharge might work. And now I would like to focus on the centralmost part of the magnetosphere, pretty close to the stellar surface. As I said in the previous part, there is a magnetospheric current which is set by the twist of the toroidal fields, and by the global twist of the magnetic field lines, and by the toroidal field V5, which is shown here at the open field lines. And this twist generates magnetospheric currents, which is compensated by the plasma flow in this magnetosphere. But if in some regions the density falls this low, we call this region's gap, falls this low that it cannot longer compensate this magnetospheric current, the electric field, parallel electric field starts growing in there according to the Maxwell equations. And this parallel electric field extracts the particles from the stellar surface, accelerates them along the band dipole-like magnetic field lines, which leads to the emission of the curvature photons, of the very energetic photons, which also propagate along the band field lines, and when they accumulate some angle with the field lines, they get converted into electron-positron pairs, or the secondary pairs. And because each of the primary particles accelerated from the stellar surface might emit lots of secondary curvature photons, and each of them gets converted, we eventually get some high density clouds of the secondary plasma like shown in here.
You also see, I think, just on the secondary discharge, which barely popped up. It wasn't nice. You see that?
That's a very difficult question, actually, if we can trust. There is this idea of the outer gap, but I cannot trust myself that this is, completely true for the reasons I'll show a bit later. The good news for us, speaking about this model of the discharge, is that we know that the distribution of the magnetospheric currents on the polar cap, as it's shown here, for example, with the inclined radiative, can be just interpolated from the global solution of the magnetosphere, which can be obtained from any reasonable either theoretical or like force-free models. And here we can see that these magnetospheric currents can be either positive in terms of Galdiak-Julian current or negative, also in the same sense. And then not too much different from one. So it's just from minus few to few. And to better understand how the discharge works, I can show you some main steps of how the discharge evolves. So here, for the case of the superconducting current, I start with 1D simulation, with the electric field, parallel electric field being on top, and this is the phase space of the particles. So when there is a lack of plasma in this region, the electric field starts forming, which is not very large yet, and this accelerates the particles in a different direction, the positive one and the negative one, to the pretty large Lorentz factors here is around 10 to the 5. On the second stage, the later times, lots of this beam keeps accelerating and lots of the curvature photons are being emitted in here, which are shown by the black lines. And when they start converting into electron-positron pairs in here, shown by this by this red and green dots, the density starts growing and the electric field starts screwing up. So this small bump on this electric field because it goes to 0. And then later in a linear stage, lots of secondary particles is produced and the electric field in this region is fully screened. The assumption is that this moment of the screening launches the wave, which eventually evacuates from the magnetosphere. And we see this as a coherent radio emission. Okay, as I said, there are different magnetospheric currents on the polar cap. And for the superconducting field superconducting currents, which are larger than 1, the creation of the secondary plasma, which is shown in here, as the ratio of the background density. This cloud is very dense with the multiplicity of around 1,000 for these parameters, and it propagates outward with a very low density tail trailing behind the main cloud. In the opposite, for the return current, for the negative current, the gap opens at the high altitudes, which here is the upper boundary of the domain. And it produces this very dense cloud of the secondary plasma, which propagates towards the star. So now let's hit the star, which is on the left, and only low density part with the density of around a few Galdiak-Julian density, the typical densities, propagate outward and probably supply the outer magnetosphere. So far, the theory of 1D discharge seems to be well established, but people still lacking of understanding how the more realistic two-dimensional or even three-dimensional discharge will behave. For example, it might be responsible for the different variabilities which we observe in the radio emission. For example, if we keep tracking this radio beam for a long time, for many hundreds of pulsars, as shown here, it experiences some semi-periodic motion, like it drifts across some zone. One of the theories, which was proposed by Ruderman Sutherland in 1975, proposed that the actual discharge doesn't happen on the whole stellar surface, or its polar cap surface, but actually in a bunch of isolated sparks, like shown in here, which are separated by the vacuum regions where no pair production and radio emission happens. and this spark are drifting across the polar gap in some sort of regular manner. The idea behind of this is that if we have a flat capacitor, there is some potential in here, which is comes from the solutions of the Poisson equation. But if we insert some conductor, it limits the transverse size that much that the potential drops significantly in this house. And this low potential is not longer capable of maintaining the pair production. But the question is, if the sparks can actually exist, can they survive, and what is the characteristic size of these sparks? Because for this representation, it was assumed that the discharge is stationary. But actually, I showed before that this is not stationary, but rather intermittent. To see how this isolated sparks can survive, and if they can survive, I will show here some of my simulations where I simulated a 2D polar cap with some imposed distribution of the magnetospheric currents, which pretty much corresponds to the symmetric, to the aligned rotating when the rotational axis and the magnetic axis of the pulsar are aligned, so in the same direction. And to get rid of the initial synchronization, I split the polar cap into different patches, which are shown by the green lines in here. And some of these patches have reasonably low density, that the gap formation of these plasma zones can start forming there pretty much instantaneously. But in the other zones, it happens later. So there is no initial synchronization in between, like these different patches can arise, and if some synchronization will appear later, it will appear there self-consistently. So initially we have only 3 patches available for the discharge. One in the zone of the positive current, like here, and 2 more in the zones of the body of return current. We can see again that the plasma blobs propagate from the upper boundary towards the stellar surface.
It's kind of same set of Sasha.
Which Sasha, sorry?
Also, radio emissions.
2D. Yeah, he was rotating his 2D. He was rotating his 2D plane, and he didn't try to set up any desynchronization. So whatever happens was synchronized by the idealized initial conditions. Okay, and at the later times, we can see, for example, here that when some of the patches are available to discharge, like these ones, and some are not yet, some of these dischargers already operate on this intermittent regime, producing these isolated clouds of the dense secondary plasma, particularly in here. And some not yet, they are like rather operating some sort of stationary regime when the photons get converted to electron-positron pairs far away. And here there is some electric field zones, which are probably not yet very well seen. But let's see what happens later, when the patches in between become available for the discharge as well. Then the electric field in between these zones start communicating through these vacuum episodes. Its amplitude is growing, because as you can see from the color. And also all of these discharges switch into the intermittent regime. But if they are in the intermittent regime, this means that the lifetime of the electric field on the field line is finite, pretty much determined by the gap size divided by the speed of light. And if 2 field lines are like too far away from each other, so the signal between them cannot travel during the lifetime of this electric field, so during the lifetime of the gap, this means that these 2 electric fields don't know about each other and cannot get synchronized. Probably this means that this natural coherent scale across the field lines should be comparable to the gap size. And there is this synchronization in here, and also the complex shape of these clouds in here probably hints that there is some lack of synchronization. And there is some extreme case. If the transverse scale of the gap, the coherent scale of the gap is comparable to the gap size, this means that for the weaker pulsars, pretty close to the depth line in here, when the gap size is comparable to the size of the polar cap, this means that the coherence in there, transverse coherence in there, should be very dramatic. And let's see if it actually happens. Initially, we have again a few patches available for discharge, but they cannot produce the pairs yet because their potential is too low. But as soon as they start communicating with each other, when the intermittent patches become available for the discharge, the potential increases, and they communicate across the whole zone, creating a reasonably coherent cloud of the secondary plasma which flies away. Again, so here is the field is growing because the transfer size is growing, and here is the creation of the secondary plasma. Okay, so far we saw some desynchronization of the field lines, but this desynchronization was not very well pronounced, I would say, because the gap restarts too oftenly, and it was a bit of parasitic. So, like, one electric field might be communicating not with exactly the same discharge, but with the previous or the next one on the other field lines. But what we know from the recent observations by NASA collaboration, that if the discharge actually restarts as often as we expect from our simulations and from simulations of others, then we would see that the NASA collaboration would see much brighter X-ray emission from the polar cap of the pulsars, because the surface gets heated by the particles, which is accelerated in these gaps and bombard the surface of the neutron star, heating it up. And this factor of this overheating would be by a factor of about 1,000 for the most energetic known pulsars, which means probably that the easiest way for us to feed these physical parameters, the observational parameters, into our model is to assume that the discharge restarts not every L gap over C, but not that often. Which probably there should be some physical mechanism which remain this gap closed for a longer time after the discharge event. And what it could be, there is a hint in here in this toy model. So this is the unscreened electric field shown in here. And this is the plasma cloud which I inject by hands into this electric field with the phase space showing. And we can see what happens. So the electric field gets screened, but it doesn't fall to zero exactly. And there are some oscillations in there which thermalize some fraction of the injected plasma and create this relatively low density tail behind this cloud. And if this tail survives for a long time, it can screen the electric field behind this cloud for a longer time. And if this is the case, let's see how the communication, how the discharge synchronization would happen. So here I just inject by some artificial tail by hands behind the cloud, some window behind the clouds of the secondary plasma. So there is a discharge event, and there is a long tail which I inject by hand, so it increases how often the electric field reopens, particularly in here. And in the later stages, we can see that discharges still happens on the different field lines, and they still try to communicate with each other, but they fail to do so because the discharges from the different patches, just electric field from the different patches, don't know about each other because they live in a different time moments, and they remain this unsynchronized, producing this sort of more chaotic distribution of the clouds of the secondary plasma.
Would you go about to derive a physical length of that? I guess A for first principle and B for most.
It's complex, right? Because it incorporates the energy of the secondary pairs. Also, the fact that this energy decreases with distance. It also incorporates how quickly you load the plasma into this electric field, how quickly the amplitude of these oscillations decreases. So there is some complex interplay, which probably can be approximated by some works like Libby Tolman did in 2022, but she didn't do it completely, so she just saw some normalization of this electric field.
So what is the order of magnetized in this stuff called, right?
It's a few in the best case.
So it's just roughly enough to screen.
Yeah, it's just enough to screen the electric field. Yeah, because even like the discrepancy level of 10% is going to be enough to restart the gap or to shut it off. This is probably the most realistic case of a 3D discharge with the magnetospheric current distribution corresponding to the inclined rotator with around 60-degree angle between the magnetic axis and the rotational axis, which is expected for the pulsars like Vela. And then here the half of the polar cap is occupied by the zone with a positive current, and the other half is by the zone with a negative current. Here is the video showed two different slides of the density along the field lines and also in the surface of the field line, parallel to the surface of the neutron star. And we can show again, here is the electric field, that for the discharge on the positive lines, the potential is that small that it has to wait until the other patches become available to start the discharge. So everything is synchronized and produces very coherent clouds. While in the zone of the return current, the potential is pretty large, and all of these isolated patches are pretty much incoherent and don't know about each other, producing these complex clouds like shown here. Here is the volume rendering, this one large coherent cloud of the plasma of the field lines with the positive magnetospheric current, and some more complex structures, not even that regular, corresponding to the zone with the volume return current, where the gap is pretty small and the coherence length is also pretty small. So coming back to our problem about the production of this very high energetic emission from the current sheet. Now we know from the global solutions for the pulsar magnetospheres that the field lines which actually feed the current sheet, so like this outermost, possess the volume return current, shown here between this dashed line and the red line. Which means that at these field lines, the discharge, wherever it happens, probably somewhere in the inner magnetosphere, where the clouds propagate inside, it pushes away only a small fraction of the produced density. This is actually what Ashley might have seen. So it's like a very small fraction of clouds which he had. This is like a multiplicity of around 10, which means that only like a few particles fly back, and this might look like a vacuum on an outer gap for us. But I'm not sure if this is actually the case. So these low-density clouds propagate backward and actually feed the current. But now we have another problem. If before this we had the expected magnetization of the upstream around 10 to the 5, which was too low. Now, if we assume that the multiplicity of this plasma is just few, this means that the magnetization of the upstream of this current is too high, around 10 to the 9 instead of desired 10 to the 7. But we don't see this sort of the emission from the synchrotron part of the spectrum. Which probably means that if the current sheet is not fed by the discharge, it has to grow up and find the food itself. And here is the model how this could happen. So there is a current sheet which produces the energetic synchrotron photons, as we discussed in the first part of the talk. And these photons are flying away. And while they are flying away, they might collide with each other and produce this gamma-gamma or Breit-Wheeler process, which produces the secondary plasma. For the pulsars like Vela, which I was talking about, the cross-section of this reaction is very low. It's around 10 to the minus 6. But the number of the photons is that large that it might actually significantly modify the density of the plasma in this immediate upstream. So if it produces some secondary plasma, they are produced with non-zero energy, the new particles, and these particles are emitting synchrotron photons themselves, just orbiting in the upstream magnetic field. And these synchrotron photons should be also pretty soft ones. And they produce lots of soft photons, which can be scattered by the energetic particles from the current sheet when they fly towards the current sheet. And this might produce the inverse Compton signal. So in this model, let's just approximate whatever the spectra we measure from our simulations. either some theoretical one with gamma minus 1 for the part of the spectrum which is where the cooling is inefficient, and then stepping to gamma minus 2 when the cooling becomes efficient with the cutoff and the Lorentz factors corresponding to sigma. And this is prescribed synchrotron photon spectrum with the cutoff corresponding to our theoretical model is 16 maybe sigma over gamma c, which is pretty similar actually to what we measure from our simulations. Okay? So then, when these primary photons are shown by the blue line and here the right plot propagate away, they start injecting some secondary pairs. This is this dotted line and dashed line and here in this particle spectrum corresponds to the produced, the injected function of the secondary particles. And these particles, they either cool down or fly away during like the light crossing time. And then this is the stationary distribution function of the particles, which is subject to the cooling, to escape, and to the injection to the source function due to the gamma pair production. And this distribution function can produce this sort of the soft photons with the energies of just few electron volts or few hundreds of electron volts. And it turns out that these particles are most efficiently interacting with the most energetic pairs from the current sheet. And so they interact more efficiently if their energy is pretty much inverse proportional to the energy of the pairs. And this produces the inverse Compton signal. Here, with the extent of around tens of GeVs, as we expect, with the energy ratio of these two peaks, of the synchrotron peak and the inverse Compton peak, is around 10 to the minus 4, which actually corresponds to the observations. So this theory, in the case of the inefficient pair production above the current sheet, seems reasonable for the Villa emission. But, for example, it doesn't explain at all what happens in the Crab pulsar, where this pair production is way more efficient. And the spectrum actually shows no very bright features, which is shown by the dotted line. And here, still, it expands the energies of a few TeVs, which is very energetic for the pulsar magnetospheres. Okay, and I think this is my last slide, my takeaway points. That we know that the current sheets with the strong cooling can produce the very high energetic photons with the energy above the theoretical limit of 16 MeV, or the burnoff limit. And these photons, the most energetic photons, are mostly propagated along the current sheet, along the direction of the upstream magnetic field of the current sheet. And this one, together with our understanding that the gap, how the gap works, that it works in the intermittent regime, which produces the plasma in the magnetosphere, help us to understand how the current sheet can be producing the emission for itself, can be producing the plasma for itself and self-regulate to produce very energetic emission, which was detected recently. I think that's it.
Okay, I think we still have 10 minutes for questions. Is there any questions among the audience? And also the online audience, if you have any questions, just post it in the chat and I can read it out and let's start.
So to my understanding, you only talked about isolated pulsars.
Yes.
Maybe this is a naive question, but like, have you ever considered a pulsar with a binary companion and how this impacts the magnetosphere? Is this understood?
Well, I guess whatever I was talking about, not the current sheet part, but rather the discharge part, would be significantly contaminated by the inflowing matter. Particularly because even if the matter falls to the dipolar field line, it cannot drill through it and have to fly along the few lines and probably fall onto this polar cap. So for the current sheet, I don't think it really matters.
So I remember that in Mark's paper about that one charge, I think he has an assumption about the free path of the photon and the polar cap size, right? Just assume it to be like comparable at least. So that should be the case for the energetic pulsar. But for slowly rotating pulsars, do you guys have any intuition about how the multiplicity eventually can come up from this polar discharge and how much of them can remain in the cluster?
Well, yes, you are right, but whatever. So this is a few questions actually, and then a few answers, I guess. For the what is shown in if we look at this PP dot diagram in here, this depth line was theoretically derived from the assumption that the gap size or the mean free path of the photons, so the most energetic photons, cannot be larger than the polar cap. So this assumption is somehow justified, but this doesn't have to be true. Like, even if like the zone of the electric field is still limited by the transverse size, it cannot grow like indefinitely. But the photons still can propagate further away and produce the pairs, the large distances, which means that this is like not the depth line, but the depth valley. Like these pulsars are lying below this line. And if he actually used, in his paper, he used lots of different channels which can produce the pairs. I think like the pair production by the synchrotron photons, which are emitted by the secondary pairs shouldn't exist for the weaker pulsars because it's too inefficient and the mean free path is going to be like huge. So, but we can easily get the multiplicity of around like from this secondary cloud from just this curvature emission, which can easily be like a few hundreds or even thousands. So like the 10 to the 5, but 10 to the 3, the short answer.
And also the periodicity, how does the periodicity relies on?
This one, I don't know. Nobody knows. But if the photons are produced above the zone of the electric field, they don't fly back and they don't screen the electric field. So probably this would operate in some sort of stationary regime.
I will have a question. So if you jump into the last slide, the item 2.
This slide?
The very last slide.
This one, okay.
From this, the photons of light energy, presumably like the delta T and all of it. So for example, if you consider equatorial correction outside the cylinder of a pulsar or something, is that kind of telling us that if we see very high energy flows that come from, can we something like say, okay, we're looking at this pulsar like a equator?
Yeah. Yes, this is right. So for the inclined rotator, the current sheet is in the magnetic equatorial plane. So when it rotates, the plane like vibrates like this, produces like the wavy-like structure. And when we see probably of this some part of this current sheet, this one, when it shines towards us, then we see the peak emission.
I'm not sure this is practical, but in principle, that can be created with other observations to constrain the inclination spectrum
Yes, you're right, and this is even used. Not the 20 GeV emission, because like after like tens of thousands of the rotational periods, they only catch 20 photons, something like this. So it's not a statistics yet. But for the gamma ray emission, yeah, it's used together with the position.
So on that point, they both have to be moving in a different direction. Is it like out of phase consistently with high energy photons because say the curve sheet?
Yeah, it's out of phase. Yeah, this is what is actually seen in this light curve, right? Yeah, it's probably be easier for me to just. I know I cannot So yeah, here, this is the bright emission. So like this red and the blue line show the peaks of the high energy emission, which probably comes from the current. And they are completely off peak with the radio emission. There is something about the pulsars like TRAP, which has not one radio peak, but like 6 or 7. And some of them are with phase with the high energy emission.
That applies the radio emission crash.
Presumably.
So you need the collision of.
This is the theory, yes.
Another scenario. Imagine the plasma supply was decaying over time. Express amounts of black holes.
Okay.
So you basically also have the current sheet is decaying exponentially. The plasma source is not decaying. Not have discharge. I could still have spark discharge. Like all news would be not. I wonder like what would happen in this spectrum.
Well, if the pair production decreases in time permanently, so we will observe some dead pulse, right? Or we rather don't observe it, probably with some. But you mean how the communication between the current sheet and the discharge happens?
No, just in terms of the high energy emission correction. I mean, in that case, we would also worry that the electricity is so high. Basically,
oh, you mean like just there are like the stripes with the.
Exactly. I'm wondering if you have multiple stripes, but plasma supply goes down.
I have some assumption, but this crab emission, which I show, it might be actually something like this. But the limiting cycle might be, yeah, like spectrum, like, where is it? Sorry. Yeah, like this spectrum. So in here, it's sort of might be something like this. In some limiting cycle here, for example, if there is like the burst of the pair production of the current, then everything shuts off. It's in a weakly cooled regime, it doesn't shine. The plasma flies away and it restarts. If this happens something like this, we can just like see some accumulation of the different emitting regions, which mysteriously sign up with some sort of coherent line. But this is hand waving.
Yeah, let's take this.